Welcome back to the Explainer. Okay, today we are tackling a classic coding puzzle. Now, this is one of those problems that seems kind of tricky at first, but it has this just surprisingly elegant solution once you see the key insight. So let's just dive right in. Here's the challenge. We're given a linked list, right? This jumble of numbers you see over on the left, and we're also given a pivot value, which in this case is the number 3. Our job is to rearrange that list so it looks like the output on the right. You can see how all the numbers less than 3 are now on the left side, and all the numbers greater than or equal to 3 are on the right. So, formally, this is what's known as the partition list problem. The goal seems pretty clear, right? Split the list into two parts based on some value x. But, and this is a big but, there's a crucial catch that makes this way more interesting than just, sorting it. And here it is. This slide shows you the real challenge. We can't just move numbers around willy-nilly. Look at the original list. You see that first 2, and then later on there's a second 2? Well, in our final output, they still have to be in that same order. Same thing for the 4, 3, and 5. We absolutely have to maintain the original ordering inside each of those 2 new partitions. So that's the real question. How do we do it? I mean, if you try to start shuffling nodes around inside the list itself, oh man, you can end up with a complete spaghetti of pointers. It gets complicated really, really fast. There's got to be a better way, right? And you know what? There is. Instead of trying to fix the original list, we're going to take a much cleaner approach. We're just going to build 2 brand new lists from scratch as we walk through the original one. It's simple. We'll have one list for all the nodes with values less than x, let's call it the left chain, and we'll have a second list for all the nodes with values greater than or equal to x. We'll call that one the right chain. This one idea just simplifies everything. Okay, so let's get our hands dirty and actually walk through our example. You'll see exactly how this 2-chain strategy works in practice. We're going to go node by node. All right, we start at the very top of our input list. The first node has a value of 1. And for every single node, we ask an incredibly simple question. Is its value less than our pivot, which is 3? That one little question tells us everything we need to know. Does it belong on the left or on the right? For the number 1, is it less than 3? Yes, it is. So we add that node to our left chain. The right chain is still empty. Easy enough? Let's keep going. Okay, the next node in our original list is the one with the value 4. We ask that exact same simple question again. Is 4 less than our pivot value 3? Well, no, of course not. So the node containing 4 becomes the very first element of our right chain. See? Our 2 lists are starting to take shape now. Okay, next up, we hit the node with the value 3. Now, you gotta remember the rule here. It's greater than or equal to x. Since 3 is equal to 3, it belongs in that right partition. So we just tack it onto the end of our right chain. Let's keep this train moving and see how these chains build out. The next node in our original list is a 2. Is 2 less than 3? Yep. So we append this node to the end of our growing left chain. And notice, the 1 is still before the 2, just like it was in the original list. The order is being preserved automatically. We're almost done with our pass through the list. The next node we're going to process has the value 5. 5 is definitely not less than 3, so it gets tacked right onto the end of our right chain. And again, look, the relative order of 4, 3, and 5 is perfectly preserved. And now for the very last node in our input list, which happens to be another 2. This second 2 is also less than 3, so it gets added to the very end of the left chain. This is just a perfect demonstration of preserving that relative order. The first 2 we saw is still ahead of the second 2 we saw, and just like that, our 2 chains are complete. So we've made one single pass through the original list, and now we have these 2 perfectly ordered sublists. The last step is it's almost laughably simple. We just need to connect them together. In the actual code, it often just boils down to a single line that looks something like this. What we're doing is we're finding the very last node of our left chain, that was that second 2, and we're telling its next pointer, hey, you now point to the very first node of our right chain, which was the 4. So we just link the last node of the smalls list to the first node of the bigs list. Then we have to make sure the very last node, the 5, points to null, to signal that's the end of the list. And then we just return the head of our beautiful new combined list. That's it. So let's just step back for a second. Why is this method so effective? Why is it so much better than trying to mess with the original list? Well, this approach is just beautiful because it naturally satisfies both of the problem's rules without any extra effort. By simply appending nodes to our two new lists, we automatically keep their relative order. We do it all in one single efficient pass, and we avoid all those headaches of rewiring a list while we're walking through it. It's just clean. And this really brings us to a final thought that goes way beyond just linked lists. Sometimes the easiest way to rearrange a room isn't to push all the heavy furniture around. It's to move everything out into the hallway and then place each piece back in exactly where you want it. It kind of makes you wonder, right? What other complex problems could be simplified with that same basic idea?